Hello students, welcome to solution of yet another challenging problem from the challenging problem series or weekly challenge problem series, right? So in this question, this ring A ring or the black ring is fixed while this ring B is being rotated with angular velocity omega about this point O, right? So this one point is already at one of the intersection points of the ring. We have to determine the maximum and the minimum speed of this other point of intersection P point, right? So let's come to the solution part, and I would encourage you to pause this video right away and try this question on your own if you have not tried this, right? So let's come to the solution part. Let me first make you visualize what is happening here. So as we are rotating this blue ring, the point of intersection, if you can follow my cursor here, is moving like that. One simple thing about this motion is we can right away say that this point P is moving on the circumference of this black ring. That means it is moving on a circular path and it is having a circular motion, right? So if a particle is moving in a circular path of radius r, its speed is going to be omega r, but we do not know that particular omega, right? It's not about the omega of this ring, it's about the omega of this radius vector that is making the line joining between the center. Let me not call that point O because it will be conflicting. Let me call that center point C1. C1P vector or this radius vector, the angular velocity of this radius vector is going to be used for determining the velocity of this point P, and we do not know for sure that this angular velocity is going to be strictly directly related to that particular velocity. Of course it will be related, but we do not know the exact value right away, right? So now let me switch back to another way of seeing that particular problem so that the motion of P becomes slightly less disturbing or slightly less tedious or difficult. So let me go back to another frame of reference. Let me call another frame of reference as frame whatever X, right? So what is special about this frame X? This frame of reference is a rotating frame of reference about point O, right? So this is the point O here, and the frame of reference is also, that means your observer is also rotating with angular velocity omega by 2 in the anti-clockwise direction, right? So in this particular frame of reference, the angular velocity of this blue ring is going to be equal to omega minus omega by 2, that is omega by 2, right? So omega of blue ring will be equal to omega by 2 in the anti-clockwise direction. But now in this rotating frame of reference, as the observer is rotating anti-clockwise direction, what it is observing, that this black ring will appear to be rotating clockwise, right? So the angular velocity of this black ring is going to be also equal to omega by 2, but that will be equal to in the clockwise direction. So 0 minus omega by 2, we did use the relative motion concept here, and in that particular case it will be very nice to see that this point P here is going to remain on a straight line. You can observe that. Let me help your imagination with a very simple animation here. So this is the line. What I'm proposing, that this point P in this particular frame of reference, this point P is going to always remain on that line if the angular velocities are going to be opposite and same, right? So this is the point P here. As you can see, it is moving down, then it is moving up, right? It is moving on this particular straight line, right? So in this case, let me call this point P, and we already know that the velocity in this frame of this point P is going to be in this line. So along that direction, let me call the velocity, radial velocity VR, right? Velocity of this point P. Let me do one more thing. Let me join the centers of these two circles with P and O, right? So let me join these two. Let me join these C1 and C2. You can very easily say that these angles are going to be 90 degree. And if this whole length or the distance of P from point O is small r, these radiuses are going to be equal to capital R. Let me call this angle as theta. So using the symmetry, you can say these, all of these angles are going to be equal to theta. So in this frame of reference, the velocity of this point P will be nothing but dr by dt, because it's a straight line motion, and along the radial direction the velocity is going to be dr by dt, right? So one more thing, can we relate theta with somehow any of the angular velocity of these two, right? So you can see here that this vertical line is not going to change. The line which is joining O and P is not going to rotate. So it is a fixed line. So taking it as a reference line, if I join these two centers, the angle made by the center C1 or C2 will be 90 minus theta. So as these rings are rotating, the centers are also rotating with them. That means the angular velocity of these lines will be the angular velocity of the rings, right? So d by dt of this angle, that is 90 minus theta, will be omega by 2, at least in the magnitude part. So I can write d by dt of 90 minus theta. Of course 90 is constant, so I can just write d theta by dt magnitude is going to be equal to omega by 2. Now this Vp can be written as dr by dt, and you can see here that from this right angle triangle, this length will be equal to r sin theta. This will be again r sin theta. So small r is going to be equal to 2r sin theta. That means Vp is going to be equal to 2r cos theta into d theta by dt, that can be written as omega by 2. So this becomes actually r omega cos theta, right? So this Vp in this particular frame of reference is r omega cos theta. But we had to determine the velocity of this point P in ground frame. So in ground frame, what we have to add is the velocity of this point P because of the rotation of this frame of reference, right? So because of this frame of reference, the velocity that the point P would have had because of this rotation will be in this direction, right? So you can imagine that this point P is actually moving on a circular path with angular velocity omega by 2. So its velocity along this leftward direction, that is going to be equal to small r multiplied by angular velocity omega by 2. That is the angular velocity of the frame. So small r into omega by 2, how much of that is coming out? So 2 gets cancelled. So this is r omega sin theta. And the radial velocity component was equal to r omega cos theta. R omega cos theta. So of course the resultant of these two vectors is going to be the net velocity of this point P in ground frame. And this must be actually in the frame of X, right? So this is the net velocity in ground frame, right? So velocity of point P in ground frame is going to be equal to magnitude of this resultant. That is very easy to calculate. R omega is common, so cos square plus sin square 1. So this comes out to be r omega, and you can see here that this is constant. So there is no question of maximum and minimum velocity being different one, right? So what we are getting is a very nice result, very special kind of result, that this point P is moving with constant speed r omega, right? And if you just extend that logic, we already now know that the angular velocity of this C1P vector is also going to remain constant during the motion omega, right? So that part here should lead us to think of one more solution that we could find using any other method. So I'm going to do that particular problem using another method using geometry only. That how can we prove that the angular velocity of this ring is going to be equal to angular velocity of this C1P line, right? Or C1P radius vector. So let me come to another method. Let's say at any particular instant, I have taken a picture of the situation here, that at any particular point, this is point O, this is point P, and these two centers are joined. So you can see here that this triangle is an isosceles triangle, and that is going to be very crucial for solving our question. Otherwise, it would have been not very easy to solve, right? So now we have to prove that if I rotate this blue blue ring by angle theta, this radius vector will also rotate by the same angle theta, right? And for a representative radius vector, here point O is being joined with point C2, and OC2 vector, the angular velocity of rotation of this OC2 line is going to be equal to angular velocity of this ring, right? So you can take any point on this, any fixed point on this ring, and if I join this point here with point O, actually if I am rotating this whole ring by angle theta, that also means that I am rotating this line by the same angle theta, right? So, but that would not be correct about this point P, because this point P here is not a fixed point on the blue ring, right? So it is an intersection point. It is not fixed on blue ring, right? It might be maybe we'll be getting different points of blue ring that is intersecting the black ring, right? So we cannot say that for this point P right away, right? So now let me rotate this whole blue ring along with its center by some angle, let's call theta, right? So as you can see here, if I make another such similar kind of construction that we already made, this kind of line joining system, let me join these lines again here, right? So this black center to center joining line is being replaced by this dotted black lines. This line here will be replaced by this line, and this radius vector has rotated by this much angle, and we have to just prove that this angle is going to be equal to theta. So if you want to try that geometry, you can also pause right at this moment. Okay, let me continue. Let us see this this isosceles triangle. Right, this is very easy to see. It is an isosceles triangle because this is radius r, this is radius r. So this is r, this is r. So of course these angles are going to be theta. Now you can see that during motion, this side is not rotating. This side is always fixed. So this side is always fixed. What is rotating is this line and this line. So we had rotated this particular line by angle theta. That means the new isosceles triangle, let me choose another color so that you can see here. The new isosceles triangle will be this, depicted by these dotted lines. You can see that this will also be a isosceles because this length is again going to remain same constant. So what I'm doing is I'm decreasing the apex angle by angle theta, and the decrease in the apex angle will be distributed between these two angles equally, because this is an isosceles triangle, and if the angle is increasing, both of these angles must remain same. That means the increase is going to be equal to half of that decrease in this angle. So this angle is going to be theta by 2. From here we can say that this angle is going to be theta by 2, right? Now one more simple thing, let me make two perpendicular line, and let us consider that these lines are acting as a rigid body. So if I am rotating this particular line with angle theta, so this line will also move with same angle theta in the same sense, right? So this green line is perpendicular to this black line. So if I'm rotating this black line with angle theta by 2, actually the green line which was depicting the line joining this point P and O, that line will be shown like this in this diagram. So this green line will also rotate by the same angle, that is theta by 2. And now you can see that this arc here is making angle theta by 2 at point O. So of course it will make double the angle at the center, that is theta, and that is how we have proved that the angular velocity of this ring is going to be angular velocity of this radius vector. So velocity of point P is going to be omega r. So I hope you like this solution. If you did, please subscribe and share this YouTube channel among your friends. Thank you.